So, 6th week of the course, and I was a bit late, so we'll have to get right started. So, software maintenance, we have been now past the midpoint of the course. There's 10 lectures, and this is the 6th one, so we more or less have covered over half of the stuff, and today we will be doing talking about something which is fairly common or well-known practice in the industry, although there's not that many practical cases where it has been done. I'm talking about reverse engineering and re-engineering. Of course, if there's someone from the Chinese software industry listening to this presentation, they have a habit of doing that with other stuff. So they are probably the professionals on this topic, but it's still something that has activities or things that we should know. But like always, let's start with a quick recap on what we talked last week. So last week the topic was technical debt and things associated with that. The idea of the technical debt is that it's not actually a physical thing, more or less. It's a theory or theoretical thing of what happens when you have to take shortcuts, use approaches which aren't that good, or simply lack the experience or knowledge to develop things to the degree where they should be. Of course, this means that the product loses some of its end quality or perceived quality, and over time you have to take measurements in maintenance to pay back these shortcuts and things which affect the usefulness or customer opinion or user opinion of your product. But anyway, the important thing was to remember that it's not always a negative thing. You always have to take some debt, technical debt, to complete anything, because you will run out of time, out of money, don't have all the right people or the optimal amount of people available to you at all times. In fact, usually we have been doing surveys on software industry, and we know that, for example, in the Finnish software industry, the projects tend to have something between 60 and 75% of the optimal resources. Meaning that for each project you almost always have something like 2/3 of the people you would like to have, or you have 2/3 of the money you would consider that would be more than just enough to do this properly, or you have only 2/3 of the time to complete all the tasks. So you have to live with that. And this of course means that you will have to take the 1/3 of the project as a technical debt, which you will be paying on the software maintenance phase. We're also talking about the refactoring work. So when we have to fix something or recreate something, make it better, make it more maintainable, make it more usable, and these sort of things. The idea was that we don't actually change how the module behaves. We just make it or recreate the part as it should have been done in the first place. This is actually something that we are continuing today with the topic of reverse engineering and re-engineering. These are basically the same things, or the different flavors of the same activity, because that's more or less one of the main things that you have to do when you are maintaining a legacy software. If we are working with something that's falling out of support, or not the product itself, but for example the platform or the architecture or the development tools or the database or whatever, you have to do these things to keep using or keep delivering your product, even though the original tools no longer exist. On this aspect, for example, some computers or computer systems which were designed in the 70s or 80s or early 90s are still developed for industrial automation, because the robotics and automated manufacturing lines are hugely expensive, but they are only designed to be used by that one particular closed system computer. So if the computer has a lifespan of 10 years and the factory or manufacturing line has the lifespan of 40 years, then it means that you actually have to be able to get the 40-year-old or 30-year-old computers or computer systems compatible to that, because you need to have a legacy support. Of course, if you are making automobiles or planes, you have money, you have influence to do that, but if you are just doing some software development or app development or whatever, you don't have the luxury of doing that, so you have to come with the ways to keep or rig your system to keep working. Also, there were a huge list of things compiled here again, which are more or less the design patterns of things that probably are caused by the technical debt, or bad design, bad architecture, inexperienced work. These sort of things. The list is huge. There's actually more of them. If you Google around, you will find the design patterns for what type of code smells quite handily. And of course, this changes between the programming languages and environments to some degree, because not all environments or not all languages allow every type of thing listed here. For example, things like interface classes or abstract classes are sometimes missing on some implementations of object-oriented programming language. So, of course, there's some special cases. This is also why I told last week that you should probably look for the things that affect your project when the time arises, and we don't spend time on these lectures or on this course to memorize all these different design patterns or design anti-patterns which are harmful to your software. Anyway, that leaves us to today's and this week's topic, the reverse and re-engineering. Like I mentioned before, this is something that continues from the last week's topic, and these are also a bit similar things in general. Usually the reverse engineering is part of re-engineering work or something like that, but we'll get back to that in a couple of minutes. So, during the lecture slides themselves. So let's see what this thing is all about. So, what is reverse engineering? Usually, reverse engineering is needed when you are stuck or are in a very, very bad situation in your project. The simplest situation here, and actually something that we are sort of trying out on this week's exercises, is that you have a Java file. You have made a program, it compiles, it runs, everything is smooth, perfect, but then you accidentally destroy the source code. Okay, that might be annoying. I have seen actually one group do it in one game jam code camp. They weren't really pleased that they accidentally overwrote everything on their version control system. I still don't know how they managed to do that, but hey, I don't blame. I'm just a lecturer here. Anyway, you lose the original source code, and then you have to maintain your product. You have to make changes. You have to keep living with the fact that you no longer have the accessibility to the source code itself. It might be also because the program is so old that it no longer exists anywhere, or you are just using some module which you have been given from one version to another, or migrated to one version to another, and now you are stuck with the situation that you actually have to check something or make some changes. So, how do you do work with this sort of situation? So, of course, you only have to compile software, which means that you have the output available. So, usually, if we develop software, we start from the requirements through the design, implementation, testing, and so on, like we have been doing, or at least talking about, for very, very long time. But the idea of reverse engineering is, well, simply the fact that we do things in different order. So instead of going from the requirements to design to source code behavior, we actually do it in the opposite order. So we have a software now. We try to decompile out a source code if that's possible. If it's not possible, then it's a very bad situation. But anyway, we can also see from the behavior something that how it's probably made, or what sort of things it has to do, and also collect requirements, what sort of aspects does it need to, or modules does it need to connect to. What sort of database is it using, what sort of inputs is it taking, what's happening in general, but it simply means that we are doing software engineering in reverse order. We start from something that exists and try to decompile out a source code, which probably isn't exactly the same thing that we had before, but probably does all the same things. Of course, if we have some stubs or parts which are very fringe cases or simply are not in use, they were developed for some next thing but aren't actually that useful, we might not get those things back, but still we get something back, hopefully, and we can redesign or remake the architecture, perhaps collect the requirements that we need to do, and then fix the existing software. I'm not naming anyone, but for example, the reverse engineering, this first step between from behavior to source code, actually is the most usual way of doing reverse engineering. I know for a fact that at least on one industrial automation system, the entire source code was written by internal development team based on the things that the automation tool does, because the backup or original tapes which contained the development code failed, and the system required heavy tailoring to be useful on that particular plant. So they had to remake everything at that plant because they didn't have anything tangible to start with. Of course, this was a non-intended activity, and you can guess that this was something that was not communicated towards the management or the higher ups in the system, that everything is fine except that we as a information systems management team lost the source code to everything that runs this entire plant. Well, it's a pretty tricky situation, but I think it's very, very, very many years ago, so hopefully no one gets an idea to track these people down or try to guess who I'm talking about. Anyway, so the idea is, of course, that we have an old system which we really cannot rely or access, so we have to make an abstraction system, something that does the similar things, and then based on that develop a new system. It's not a magic trick or anything like that, it's just that we are using the old system to collect requirements or even try to recover or salvage parts that we could use in the later product. So basically, it encompasses all the activities that we are doing, trying to find information about the existing product. There's a wealth of tools, they are listed in the later slide, which we can use to, for example, decompile stuff or try to get the product, get access to the internals of the product. We can use analyzers to find out what sort of messages or network traffic the system is generating. We can even also try to use tools which try to intercept messages between the objects and these sort of activities to see or pull out information on the interfaces the system is using. And these, of course, are very technical things. We can also try to decompile the system code or machine code. But in general, even if we are doing something simple, like just trying out different inputs and what sort of output do they generate, we can also say that this is also reverse engineering, because these are all test cases or use cases which we need to solve to find out what actually is going on in the product or the source code itself. For example, on this week's exercise module 1, you are given a source code or compiled Python code, or well, Python machine code because it's interpreted language, and you have to try to recreate the source code, or at least understand what it does, and explain what it does, draw out the UML diagrams, even try to reprogram or recreate the source code based on what you saw. Anyway, of course, this is an exercise which is high risk, high failure rate thing. We can of course get some information out of it, but it's very implausible that we can actually recreate the lost source code once we are in a point where we are trying to do this to salvage anything. Of course, this means, of course, that we have to recover the lost information, or possibly, hopefully, get a proper system documentation made. Also, if we want to identify side effects, anomalies with something that was delivered to us, if we are buying our external modules or using something that was developed by a third-party company which no longer exists, there might be a problem that we don't have access to their source code because we never bought them. We never had any right to use them, so we are just stuck with a product which we have to use but isn't doing something useful. So we try to paddle upstream to see why is this giving us faulty information and how it works, so we can fix these or use Band-Aid to get around these limitations or problems in external modules. Because of course not everything by us is usually available. Not everything that we use is always available as a source code. For example, in software outsourcing activities, even though the open source approaches are favored because they are available and free, basically, if you are just including them to your product, but sometimes you are buying something that does things and then you have no control over what it does. A simple thing here, something like PDF conversion tools. Adobe really doesn't want to give you this information, and it took years to actually make credible or good open source tools because you basically had to reverse engineer everything in this aspect. Also, something like, computer security stuff. There are still used algorithms which officially don't have documentation or explain how they work. We just have guesses or plausible guess on how it should work or how it seems to work because we have created a system which always produces the same output from the same input. But this also means that, for example, if you are in a situation where you can't buy something or can't get access to something, you have to recreate things or guess things, and if it affects your maintenance work, for example, you have to make it work regardless of what happens. Usually when you are dealing with legacy systems, this is also when you need to work with these things. Also, well, if you are migrating to another hardware software platform, that's also when you probably need to probe around your own nice little cozy environment. So this is also a place where you might need to do that. So, of course, reverse engineering, the benefits here are from existing literature. I personally don't actually agree with some of these items here. Well, basically, the maintenance cost savings here mean that if you can reverse something to the degree that it actually works, or we have an example, for example, on decompiling a simple Java program, then yes, of course, it saves money when you don't have to recreate the module from scrap. Also, software reviews facilitation. If you have ability to reverse engineer or decompile your software or system or some existing legacy part, fix that and use it in your new migrated software, then of course it facilitates reuse. But the competitive advantages, I think this is more or less something that's troubling from the legal point of view, because it more or less says that you should take your competition's product or software or try to get access to that and then reverse engineer it to see how it actually works. Of course, I can't recommend you to do this because I think it's actually illegal, but still, it's something that you might want to consider if you are working in a real world. But remember that I didn't tell you this. Anyway, also quality improvements, for example, finding out if you are using something that's given to you with a word of God or someone else, that you have to use this, or this is the accredited version of this module, we don't get the certification for something, for aviation or something like that, unless we use this specific part, then we can improve our own quality by trying to find out why or how this works, or what are the limitations, or why does it break down after a certain amount of things. So, of course, the problems are, it generates gaps. The problems in general are that we lose information on each step we take. For example, what the system seems to be doing and what it's expected to do becomes a big issue here. We only see the outcome. We don't see the internal parts, perhaps. We don't see the exact algorithms. We don't see why it works or how it works. We just know that it actually works. So on each of these states, when we are doing reverse engineering, we also have to dedicate time on understanding or trying to guesswork why things happen. Of course, this also means that because this information isn't available, legally available or realistically available or simply doesn't exist anymore, then we more or less are doing a guesswork on each step. So the mapping work more or less is a, guessing science. We sort of understand how the implementation works, we sort of understand how the application works, and we try to map the outcomes to the inputs or the requirements or these sort of things to understand why it works. This also means that, of course, we can do refactoring here. We can throw out stuff that's now unnecessary because we no longer need to care, for example, on some legacy issues, or perhaps because we no longer have some other subsystems connected, we can just cut out that branch. We might even actually get better performance out of the product, but usually we are a bit desperate when we are trying to do this, if we are just maintaining software. So basically, this also means that we can do several things. We can, there's automated tools, for example, documenting out things like interfaces or trying to guesswork diagrams, architectures, hierarchies, these sort of things, designs, what sort of things seem to be inside the product. These are done by tools, more or less, because I venture a guess that no one is actually insane enough to try to read the bytecode generated by an assembler or something like that. So usually that's the problematic area. Of course, if we are trying to reduce the complexity of the product by seeing what the assembler did and trying to optimize it, then we are doing re-engineering work, which is sort of a bit of a reverse engineering activity, but is trying to achieve something bit else. Of course, if we are trying to salvage whatever we can, we can also try to identify the components or stuff that we can actually still use. For example, if we are decompiling existing product, we might try to see if we can isolate the libraries or something like that, or identify the libraries or the auxiliary parts from the primary parts, so we know that the auxiliary parts probably are just fine if we just drop in new engine or new managing module into that software. Also, on some cases, if we are doing something really fancy, like guessworking why something like Amazon recommender system works, or load balancer system on a server cluster or something, we also might want to try to recover some business rules or stuff like that to ensure availability or response times, or how it collects information and these sort of things. But in general, these sort of things we can do with the reverse engineering, trying to gather understanding. So, of course, if we get the abstract version of the software, it's always about maintenance, or it might be about the evolution, we are taking it somewhere else, or we try to re-engineer the parts of the software because we no longer can use the wraparound approach. This means that we are running the system in the simulation mode inside some virtual machine which runs in a physical machine because we probably don't have enough performance, or we have some other problems or issues with that. This is, of course, if you still remember, this is also one of the cornerstones or immediate major red flags that the software is experiencing maintenance issues if we are running it inside virtualization. And sometimes it might be because the migration is, it's not cost efficient enough, but also sometimes because simply it isn't enough in any case. This, for example, is directly taken from the idea that you have to get 25-year-old computer to run your manufacturing plant making screws. It might be possible, or it will be possible, to recreate the entire system with modern automation tools or modern computers, but still stopping a plant and ceasing manufacturing work is a hugely expensive thing to happen, especially if you don't know when your system will be online again. So, of course, you don't want to take the risk that you have to upgrade to a new version. So, formally, there's several levels of abstraction when we are talking about reverse engineering. Of course, this isn't really the most interesting thing in the world, but still, business rules, functions, structure, implementations, these sort of things. This is more or less to remember and understand that software engineering is a huge discipline in general. Of course, if we are trying to guesswork what this machine code actually looks like in a source code, that's completely valid way of doing reverse engineering. But because we are also talking about implementing or creating software or service or other things, there's other points of information within these systems. And for example, trying to guesswork the business rules, why this works, how it uses customer information, what sort of things does it do, what's the logical and functional specifications, what sort of data does it use, for example, how is the control flow, and even the implementation, the symbol tables, what sort of memory management does it use, how can we recreate this on a modern system, what sort of source code or what the source code looks like. These sort of things are all levels of reverse engineering. So the idea is that the reverse engineering is design recovery and redocumentation, making a sense out of existing system, whereas the other part of this lecture, the re-engineering, is actually trying to gather enough information from the system to understand how it works, why it works, etc., and then making something new out of this information. So the reverse engineering just tries to recover you some information or piece of things so that you can continue maintenance work, whereas the re-engineering means that you are mining for this information or gathering this information so that you can do it properly again, or do something that's 50 years old and recreate it on a new system. This is the conceptual difference between these two things. So, what sort of tools then can we have on reverse engineering? Of course, the analysis tools are the first ones which obviously come to mind. So these are the things that try to guesswork or make from the machine language code something that does similar things, or tries to guesswork what are the the logical structure of the source code, and it gives you an sort of an approximation of the applied algorithms and constructs and these sort of things. Of course, it doesn't always get everything right, whereas browsers give you ability to look to the internal parts of the software, object server, something similar, task-oriented tools to record activities, to see what happens inside the system, what sort of internal calls does the system use when it's trying to run software, what modules, what components, what operating system services is it trying to use, what sort of network communication is it trying to implement or achieve. So more or less dedicated tools to understand or see into the program after it has been created. Of course, if you know the original programming language it was made with, or even the original compiler and the original development tools and these sort of things, then the more information you have, the more accurate reverse engineering or decompiling result you will also have. There's an example of it just now, but of course, like last week, these are more or less really close to the actual programming language focused aspects. So there's a couple of sites which list tools, literature, stuff like that. On the original presentation, which I used as a reference when I was making this work, there were a couple of things from the other universities which were focusing on the research of reverse engineering mechanics or tools, or developing better tools to do reverse engineering work. So you might want to follow these links or Google around for stuff which gives you the information or ability to look into the software products. This is also something that you might want to do with the exercise assignment this week, although the program itself isn't that complicated or complex that you can't guesswork your way through and provide sort of a source code that does similar things. So applications on these tools, well, there was a huge thing on the Y2K. Of course, we don't have the same problem probably ever again, because I think it was fixed for good, at least for the next 8,000 years. So I don't guess it's not going to be a concern for any of us. But anyway, when you have these tools were developed and are developed to, well, collect information, get around the restrictions, do forward engineering after we have been given the internal parts of the software, or just simply understand what's going on and do these sort of things. So also other part besides the source code is on this aspect is the data itself. Of course, we probably, hopefully, are using databases. We probably are using something that we can access now, but if we are working with legacy systems, one of the things that we actually have to focus on migration to newer things is the data management. If we have just some old box sitting somewhere handling all the transactions and data, we also might want to consider how to access these old records, or how to get everything out of the database and re-implement it somewhere else so that we can migrate the new stuff. Also, if we are creating new data relationships, it also means that we have to collect information on what's connected to what, or what sort of database inquiries we will probably have on the existing system, so that we can have a new data server or data service or data storage which can provide these same things. Of course, if it's very fancy data, seeing that there's actually a huge amount of interconnectedness and these sort of things, it more or less has the same limitations and problems than if we were working with an object-oriented program which has low cohesion, low levels of cohesion, but where everything refers to everything else. So, considering why are we talking about data on this slide, is actually because the data recovery and data reverse engineering and data migration to another place is actually a large problem if we are considering something that's not trivial to re-implement or just take somewhere else. So there's also a number of other things here. They are just collected on this slide. The other terms. The redocumentation, of course, we have a jack sheet for documentation which is outdated. It's no longer useful. There's errors in it. It's constantly broken. So, of course, we might want to use these analysis tools to recreate the documentation. Of course, there's actually an interesting part here that it doesn't have to mean necessarily that the source code is lost. Because, well, it might be available, but considering that if we are running or trying to do maintenance work on something the size of an operating system or huge service or application or something like Firefox browser or even a physics game engine or something like that, which is basically entire user operating system almost by itself, considering that it used to overtake the entire hardware when it was running. The modern generation of mobile system game consoles are a bit different in that sense, but still they are huge software. The redocumentation might be just to generate the general level UML diagrams or list of things or list of connections or what modules or what components are actually connected to each other. So we got to gain more information or insight into the system because millions of lines of code, tens of thousands of modules or objects, there's no one sane at least, who can memorize all that information immediately and remember it so that it's actually useful or recallable information. So the redocumentation is something that we might actually do with the reverse engineering tools simply because we need to have more usable or browsable information. Well, restructuring also is something, transforming system one representation to another, while preserving its external functional behavior, meaning that we take something that was written with something modern like Fortran and trying to make it work again. And of course, why would we do that? Because we have to make something for example, banks and insurance companies or government who might have records or stuff spanning hundreds of years of information, which was just recently digitalized on the 70s. So we don't want to do that again. So we try to restructure the program with modern tools and still be able to use that same database or information. Or retargeting, porting the system to new configuration, hardware, these sort of things. That's also a thing. Business re-engineering. So we are doing radical redesign of performance to increase performance, doing these sort of things. This is also something that have been done. And reverse specification, simply we are trying to guess work based on our competition or tool that no longer exists or is no longer supported, to get an idea on what it does, why it does, what sort of things does it do, sort of things does it take into account, and how it collects information and why it uses it. Basically, fairly simple things. So there's books about these things. So if you are doing reverse engineering, at least if you are doing some reverse engineering on the things that are legacy systems or legacy supported systems, you also need to be, well, at least based on this guy, part historian, part detective, and part clairvoyant, because you can't access all the information. So, of course, there's also a list of different tools, like mentioned before, parsers, debuggers, profilers, event recorders, trying to collect you as much information on the system calls and internal logistics, algorithms, what sort of data requests there are, is it using network, what sort of things, what sort of inputs is it collecting from the auxiliary devices, It can usually, of course, I'm talking about mouse and keyboard, but it can be also something else like cameras or sensors or these sort of things. For example, on the industrial automation, the things that the system collects information can be almost everything or anything. So you would have to consider, how am I going to observe what the system that I think is recording the air moisture percentage. How are you going to collect that information, or even confirm that it's actually trying to just checking out how much water there is, or what's the moisture level of the assembly hall or something like that. For example, I know that in Nissan Corporation there are people who are crazy enough to have a clean room laboratory for the entire assembly line of the car engine, because that's supposed to be a very good thing for high performance engines. Of course, if you are maintaining a system that tries to oversee these sort of things, then, well, all these different inputs, sensors, things, profilers are your friend, because it tells you what was the actual signal that was sent in. And did the system actually use it for anything? So, well, if you have a source code, that's a very good thing. You can start with that. Use the documentation tools, or compiling tools, or analysis tools to collect as much information as you can. Of course, if you have something like Fortran code, or COBOL code, you might run into a problem that you don't actually have the tools to do test runs with that. But, well, it usually tends to be possible. Use a virtual engine, virtualization, or some virtual box, or some that type of approach. You don't have the performance, you don't have the robustness of running directly on top of the hardware, but you still have the ability to observe what it is actually doing, and you can see the source code. Of course, if it's a large system, or, well, because you probably aren't familiar with how the COBOL or Fortran actually works, because both of them were used in the 60s and 70s, you'd have a hard time to actually understand how it actually works or what it actually does. So you might also want to use some conversion tools. Of course, with that there's a problem that converting automatically from one language to another tends to be a complete freaking nightmare. For example, something simple like converting source code from Python 2 to Python 3 then at least tended to fail spectacularly, but I think the conversion tool provided by Python Foundation itself is quite robust now. You have to correct me on this one, but at least 10 years ago it wasn't that good. You'd have to double check everything it did. And if you are doing a commercial project, you probably have to do it anyway. Anyway, if you have binaries, you just have to study the existing system. But of course, there's also the legality issues here, that you might not be able to get all the information because you don't have access rights, the source code or the information. If you go to the parent company and steal the source code, that's somehow considered immoral or illegal. Even if you don't have someone you can break into and steal their stuff, there's still the problem that technically decompiling commercial software is illegal. But still, you might end up having to at least look into the system. So there's an example here on how we can actually decompile a binary, or how we can recover the lost source code. Because of this recording, I can't skip forward because I can't go backwards. But if we consider, for example, what could we actually do with these sort of things, is that we can get a baseline of source code. It's not necessarily optimized. It probably isn't even nice code. It's a sort of a back of things that happen. So more or less, if you get the reverse engineered or analysis source code generated by the analysis tool, you might look into that and consider that that is completely horrible. Of course, it's horrible because it's just something that was like basically guesswork by computer, but it's still start point of work. Of course, if you are also looking stuff, of course, for viruses, backdoors, other malicious things, you don't trust the company you took the module from. You can also use these tools, the reverse engineering approach, to try to find out if there's something strange in the system. Of course, the companies like F-Secure make products which basically do this by it themselves. They look into the machine code, look into the behavior, try to understand or see if it's doing something that it's not supposed to be doing. But of course, if you aren't running that type of company or want to trust those tools and don't want to do the security checking manually by yourself, then you might at least want to check on things that you are embedding to your own products. Of course, student works in university aren't really products or really useful in that sense. But if you are running a company which manages other people's money or do credit card transactions and stuff like that, you might also want to see if there's a backdoor in the part provided to you. But of course, these are fringe cases anyway. So basically, there's an example. This is a Java code written by, the author of the example. I just don't remember the person's name. But this was round trip compiled and decompiled by the right tools. So we started with this tool, and then it was compiled and then run through the compilation analysis tools to see how close to the original idea the tools got. So this was the first one, the original one which was made, and this is more or less what the decompiler came up with. So yeah, it's it's a bit cleaned for making any sense out of it. But especially if you compare these two things together after the lectures or from the slides from the Moodle pages, you'll see that the system actually fairly accurately replicated everything. It's more or less the same thing it was able to dig out, but of course you also have to keep in mind that this is something really simple. It's just a couple of for loops printing out variables. But still, considering that this was done completely by automation, and this isn't exactly, I think this analysis tool was 10 years, it was done 10 years ago, so the level of finesse and quality of the compilations and retranslations are probably much better now. It means that it's actually quite possible to recover source code, or at least a version of the source code which you can use as a baseline to start your work, start your development work or fixing work after that. So of course these are, humorously enough, this is from, if I remember correctly, Windows 3.1, so it's as recent example as almost 30-year-old picture. But anyway, the tools which give you idea of the static structure, architecture, even code, these sort of things have existed for a long time, and they draw you nice little graphs, and they can be then generated into UML diagrams and stuff like that. So they aren't exactly a new idea, the visualizations or decompiling a class diagram out of the system, but they exist. So, this picture is very, very old, but still gives you an idea that these sort of analysis tools can create documentation or can create or recreate the static model of the internal works of the software. Then you just have to use some other tool to make it a readable or maintainable or modifiable Java code or something else. There's also dynamic tools. These sort of things tell you what sort of calls there has been and what sort of things has been happening These are again almost 30-year-old pictures, so don't get too focused on those things. But you just have to trust me that, for example, something simple like gathering information on what modules call each other and what happens where and what are the timings and what seems to happen when something is done, or a state diagram drawn here, UML diagram automatically generated by the system is something that you can also get. If you have the source code, it's a trivial thing to have. For example, here I think the original source code was available because it uses something that's fairly sophisticated level of naming things, not just giving a abstract name for things. But anyway, now these are all the different types of reverse engineering. So, of course, if we have different things, we can try. We can also get the abstraction of different things from the software. We can, if we don't have the source code, we can try to get, for example, one package or take out the libraries or these sort of things. And there's usually some sort of automatic abstraction. If we want to see what the system is, what was the code that was actually developed for this application, if we have smart enough tools, it can also identify all the standard library stuff and throw it away. Because, of course, that's something that everyone or everything has. So it's easy to identify and easy to separate. So if you just want to see what's the new thing or what's the module that's actually doing the things in the software, it should be automatically available. And for example, another software from one research group which have been making these things for a long time. This is a program that tries to understand the complexity or structure and the different calls and branches and activities from just the bytecode available. So again, an older picture, but the code crawler has been around, and we can try to, and it can create the abstract model, and then using some programming language we want to have, even actually selecting the one we want to use, it can recreate or regenerate the structure which was derived from the bytecode available. So if we are really desperate, and if we are in a situation where we have absolutely no idea what to do, this tool might give you the framework or the skeleton to start with. Then you just try to fix things later on. So this is of course about the dynamic model of the system. The static model is what we can see from doing the analysis. Like, for example, some parts which are the libraries, which are the source code, what modules they are, what sort of calls they are. But of course, the behavior itself is something that we have to sometimes get out, and this is what the dynamic model means. So we try to get the out of what happens, how the system behaves. It doesn't necessarily mean that we get one-to-one implementation of the software, but for example, if we are trying to get the dynamic model out, we are just trying to get different events or reactions to different inputs and outputs. So if you are doing reverse engineering or trying to find out information, you should also consider, do you need the dynamic model or the static model? Do you really need to know what the Fortran source code looks like, or the links between the objects developed from the source code look like? Or do you want to have the dynamic model, which is the behavior and activities, how the system behaves or what happens when you put something in, what it does, what it gives out, and these sort of things. So if we are doing analysis on the static model, these are sort of things we can do. Measure the complexity, find out the components, do the syntax, interfaces, what sort of messages does it seem to throw around, what sort of data is it using, what's the control and data flow analysis, or well, these ifs and else's and fors and loops and stuff like that. What's the structure in general? Of course, this changes between the different programming languages and stuff. But these are the static model things. If we study the dynamic model, we try to find out, for example, how it behaves, how it manages, does memory management, what sort of performance aspects does it have? Does it have concurrency at all? For example, is it trying to do something while it's doing something? How it keeps the performance up? What sort of objects are there? What sort of method calls are there? Or even is there dead code in the system which seems to exist for the sole purpose of being there? This, of course, means that it was something that was left over. If we are doing re-engineering work later on, doing forward engineering based on the reverse engineering work, then we might want to drop the dead code, even if we might know what it is. Or if we are looking for problems or things that are backdoors or something malignant code which just sleeps waiting for the right call, these are also the things that we might find out. So if we are running software or the system with the normal operations, and there's something that simply never is called, we might also want to trace out what actually would be the necessary things to do so that this part of the code actually happens. So we might want to guess, is it some leftover stub or some testing infrastructure, which was a bad thing if you recall last week's lecture, or is it actually a real-life backdoor in the system? For example, the Chinese were very annoying people in a sense that they decided to create a backdoor into fairly popular Ethernet chipset system. If you send the right type of broken multi-call package, it simply makes every system or every Ethernet adapter connected to that particular connection to fail. It starts to wait for a call or next package which never comes through. Of course, Intel caught this at some point, but still the chipset was already distributed to several places. Of course, there's no real evidence saying that was this something that the intelligence agencies in China or military or someone else wanted to include in the design so that they can break down or cause the communication networks to fail? Or was it just an oversight on handling packages or these multi-call packages which were just broken? No one knows. Well, at least no one confesses anything. But still, if the Intel would have been looking, or the company ensuring that the chipsets actually work like they are meant to work, if they would have been looking for something like dead code or parts which are actually not used anywhere ever, they might have caught this before they were distributed around the world on millions and millions of Ethernet adapter sets. So in this sense, all these reverse engineering work, besides recovering your lost project work or your lost source code, is also something that you might want to consider, especially if you are working with something a bit more sensitive than the high scores or fanfic stuff or something like that, discussion forums stuff. So, of course, this brings us to the other part of reverse engineering. So there are tools. There are ways to recover lost information. There are ways to make the software system give out its secrets, even without actually having access to the source code itself. So what are we going to do with that information? Well, usually it's something that we call round-trip engineering. or something that's re-engineering after we have done the reverse engineering. So we gather information and then we try to make the next step on the development or the next step in the maintenance by trying to fix the system even though we might not have all the necessary parts available. There's also something that's gray box testing, which is usually called situation where we have access to one module or some modules of the entire system, but not everything in the required to make the system work. So this happens, for example, when we are providing the client software to the larger server system, which does something else or is managed by someone else. For example, if you are doing a bank software or software that connects directly into some bank's own subsystem or server, you get a stub library or included library which is documented and told that okay, this does this and this and this, but still you don't know what happens on the other side of the system. So of course, if we are doing round-trip engineering, it means that we are more or less doing the same thing on our own product or service. We have access to some parts, we are trying to fix things or provide new version of some module, so we gather information about everything else around the module and then try to recreate the new thing out of that. The example here is basically simplified version of it. It's the documentation cycle when we are trying to recover documentation or maintain the documentation based on the information we were able to gather with the analysis tools. For example, we produce source code from class diagrams and class diagrams from the source code. Of course, if we do this iteration again and again and again, we have some subtle changes in our software. We don't always catch everything. But still, this also means that the class diagram is an imperfect copy of the actual source code, and when we are making a new source code based on that imperfect copy, then we are making further more imperfect copy of the thing. Of course, this wouldn't be a problem, but given enough time, products or service or maintenance responsibilities changing hands and so on, we get all the problems we have been talking about on this maintenance course. So we lose information, we lose brains, we lose knowledge on the system itself. We might lose performance, we have problems migrating to other things, or it just takes time to understand how things work. Also, if we have some really sophisticated tools, we might be able to do some automatic translation work. But given the success rate of something like UML2, which was more or less based on the fundamental idea of this, that we create good enough diagrams so that we can generate code out of it, and then we create so great code that we can make UML2 diagrams out of it so we can visually inspect things or even code things visually. Well, of course it didn't work. It's a horrible idea. The UML2 should be used as a documentation tool to give you the general idea of how things work, and the details then are in the source code itself. But still, these are the most common things that happen in the maintenance as a source of round-trip engineering. So you design stuff with UML, you create something with Java, and of course you end up with an out-of-date documentation. You can get tools which try to maintain things or create code, but I'd say that you really in general can't trust them, or they are so expensive or difficult to use or so fringe cases that I actually have never visited a company which successfully uses the UML system as a visual medium for doing changes in the documents. They are almost always used as an archive copy of the existing architecture or system to give an idea on how everything works. So if you have to find out the modules and things that are broken or what connects to what, this type of information is usually in the UML diagrams. Of course, these sort of things are also things that you can find with the documentation tools or the reverse engineering tools, which were mentioned earlier. Anyway, of course, with these tools, round-trip engineering tools, there's also the problem that traditional wisdom says that out-of-date documentation is actually really much more harmful than the missing documentation. If you don't have the source code or you don't have the documentation, you know that you don't have anything, so you just try to find out. If you have some documentation which isn't telling you the truth or is telling you about something that seems to be quite something similar, but it actually isn't, it's harmful because it guides or steers your thinking process towards something that isn't actually working. So keep this in mind when you are trying out, or if you are trying out these sort of tools in your maintenance work. And of course, there's humoristically this the first bullet point here. I don't know why IBM spent millions upon millions upon millions upon millions of money creating development tools which generate source code automatically so that you don't have to actually know how to program. You just draw the diagrams and then the automation and artificial intelligence takes care of everything else. It might happen in the future, of course. I'm not saying that it's impossible, but it's freakishly hard to do. But anyway, like with the reverse engineering aspects, you will probably get poorly optimized, spotty code, which probably isn't something that you want to keep using forever, because that's a red flag that everything is broken in the software project. But what it actually can do is give you a skeleton from which you can start doing the development work. So even if you only have the documentation available at some point, you can, for example, take out the information from the UML diagrams. Then you might be able to generate something which can serve as a starting point. But still, the other way around, generating or maintaining UML diagrams or making changes to them so that, okay, here's the new code, here's the old version of the UML diagram, show me or give me the new version of the UML diagram, these sort of tools. Well, I'd have to accept the idea that they might exist because at least several sources on the American universities talking about reverse engineering say that these things exist, but my personal opinion is that even if they exist or even if they are being studied or generated as research items in the universities, they don't exist in real life because usually the documentation work has to be in any case checked by hand, and these automation tools either include too many details or omit too many important things or abstract things that the developer should know, even though it might not be physically present in the diagram. So we have been using the first hour talking about reverse engineering or the concept of reverse engineering, what sort of things you can do with that. So we will go also through the re-engineering part. This more or less is an extension of the reverse engineering, or what happens after reverse engineering. First of all, it's, reorganizing and modifying existing software system to make them more maintainable. Again, yet. So this is something that's more or less similar to the earlier idea which we were talking about last week, but the re-engineering itself means that you are doing a complete rehaul of the system, or at least meaningful parts of the system. So it more or less means that you are doing a rehaul of legacy system which is no longer possible to use. It's not revisioning or something to that degree, because you no longer are able to use the software or the service or the part you are recreating. simply because the support for the architecture, the hardware, the software parts needed are no longer there. So you are re-engineering a system that's modernized or can be used on more modern hardware platform. So, of course, it also means that it's easier to maintain, but usually it also means that it's actually required because there's no longer people or resources able to keep your system running. So, of course, there's on all software point of life when you just have to give up. Like with Medicare, you really should have to consider the age of the patient at some point, what sort of things you should do. But the idea with the re-engineering is that you have still some part which you need to fix so that it's no longer obsolete. Or you have some inherent use for the software. Like I mentioned on the earlier part of the lecture, for example, old databases or old data archives, these sort of things already exist, and you just need to recreate the software or update or re-engineer the product or the service which uses the existing data. So basically all these things that are mentioned come with the idea that the wraparound virtualization is too resource wasteful, meaning that it's not possible to do because it's too expensive or too heavy or cumbersome or whatever, so that you can't really be using that approach. And of course, this of course is something that you should only be doing when there's actually tools available for doing this work. The idea is that the re-engineering reduces the risk. So you start with something that exists and just revise and update that part to keep the original part usable. It's also cheaper to do it that way if you can start with a product that used to work, but it's no longer available. Like in automotive industry, if you design one engine that's very good, you tend to use it for 10, 15, even 20, 30 years, simply because you know that it's reliable and it's usable. You might want to change all the automation or auxiliary parts around the engine block itself, but you are still using the same engine because you know how it behaves. So, of course, if we are doing something for the business process or something above the source code development, this also may be because we want to make things more responsive, more efficient, or add some new feature or ability, like something simple like adding an e-store to our existing chain of normal stores. So we have the accessibility to see if the product is available somewhere or if it can be ordered from internet directly to home. Okay, so this is also a bit of a legacy thing, but these things still happen. And of course, if we need to update the existing system, we will also are talking about re-engineering because we are rebuilding something like order management system, but still retaining the same warehouse management system and billing system as we did before. But of course, the business level logistics are a bit above the idea of this course because it's something that the business people do, or it's not about software maintenance, it's about the product or service maintenance. So the idea, of course, is that we start with an existing software system, try to understand the problems and do the re-engineered solution. It's, well, not that difficult thing to get the idea of. So we start with something that used to exist or used to be the hot thing of the day and try to recreate it or reinvent or revise it to work today. That's more or less what the re-engineering work is. There's several flowcharts available here. Of course, if we take into account also things that we are doing reverse engineering, the term appears here. Of course, the original program, if it has source code available, or even if it doesn't, we can get several items of information out of it, like mentioned before. So we can get the program documentation, or the behavior, or the structure, or the other things out from it. So we know what parts we do actually have to check, and what sort of data is it using, and finally we get the re-engineered program, or data, so that we know how we should implement the new version. Of course, this is expensive, so what the idea or what the concept of reverse and even re-engineering is, that you don't want to do it unless you have the tools available. So there's an sort of an idea here is that we try to avoid doing complete recreation of the software to the degree where we are trying to recycle or reuse existing parts of the software. Of course, this is not always a possibility, but on larger systems, this is something that should be considered when we are doing a rehaul of the system. So there's a more or less idea here that if we just convert the code automatically to something else, well, that's nice. It doesn't cost much. It probably gives gives the longevity to the software and increases the software life cycle. There's also a possibility to do automated program restructuring and do that with manual changes, or do data restructuring, or do some architectural changes. Of course, the larger the change, then the larger the costs. This is given, of course. But the idea is that if we have automated tools available, then it should be simple. But if we are converting something from Fortran to Java, then you might have a bit of a problem there. Unless you have a tool which automatically adds Fortran modules to your Java program. I actually am not completely certain here, but I think that for this particular reason there are actually Fortran compilers to the common language, so that you can use that. If you find the Fortran source code, you can use them as a part of your Java program, because never throw away anything. Anyway, the idea is that, of course, the hardware platform updates, the stuff isn't anymore capable of using Fortran to maintain the software, or the last person who was capable of using the Fortran as a development language went insane or senile, so you have to upgrade your system. And of course, considering that these things are costly, and basically you have to prepare for a situation where you might have to actually even develop the entire software again, this re-engineering is only realistically possible if there's some automation behind it. For example, if you are trying to re-implement your insurance company's Fortran server system or data management system or database system into modern hardware or architecture, unless you have tools, something like Java runtime environment compiler for Fortran language available, then it's not even worthwhile to try it. It's just easier to overhaul the entire system. But if you can embed the existing parts or use the existing parts to some degree, then of course it might be cheaper to do it that way. So the translation process isn't that interesting really. So you identify the change differences, you use the translation, you oversee that everything works, do the manual translation, and then you are set. Of course, this is an ideal view and actually quite simplified version of doing an overhaul of legacy systems. Of course, this says that it's easy to do, it's easy to consider, but actually maintaining, updating, upkeeping main legacy systems is an area of software engineering business, because these things are hideously expensive. All this re-engineering work is the fact that it's only worthwhile to do if there's automatic translation tools available is actually a real concern, because in every data warehouse or every bank or every server cluster there's this one weird cabinet where there's this one old hardware system running an operating system which hasn't been supported in the last 20 years, and no one actually knows, is it only heating the room or is it actually doing something important, but no one is going to touch that particular cabinet or not even look too much into that general direction, because if it actually does something and if it fails, then the system might fail spectacularly at some point. There's actually even talks that there's in a Bank of England, there's one Cray supercomputer in their data warehouse on which it's absolutely forbidden to lean against it, sit on the bench which was built around the supercomputer, or switch any cablings or touch the hardware in any way, because they are fairly certain that it keeps doing something, but no one knows what it actually does. It might be something stupid like it's handling the modem-based dial-in transactions with something. Okay, so our customers might not be using a dial-in modem anymore, but if there's some module which sort of sends a dial-in transaction to the server without being a dial-in system and no one knows about it, then it might fail, and then the transactions fail, and then the bank is completely screwed. So it's a let's keep hoping machine that, but it's absolutely forbidden to touch that thing simply because the tools to do this step here aren't available. And if some small player like Bank of England isn't willing to pay for doing that transition work, you might also want to consider how much your local software engineering shop is going to be willing to pay for doing these type of transition activities. Actually, the Tieto building on that direction, right after the hill on the Kareltech building, is actually dedicated on doing maintenance work and these sort of activities. So if you are really into maintaining and updating legacy systems, you might want to apply for a job there. Anyway, going into the last slides, because we are running out of time, not only because I came here late. So basically, the reverse engineering we already talked, but the reverse engineering is the first step on all the re-engineering tasks. So we need to understand what the old system was doing so that we can possibly update or transfer the system to a new place, or do re-engineering work just enough so that we can get the old system to boot up in a new environment. So there's activities, so we do reverse engineering and we gather information, we get documents. Based on that, we can start doing the re-engineering work. Great. So yeah, it's usually something that's done before re-engineering, but like mentioned before, the reverse engineering is also useful on some occasions when you are just checking what the system is actually doing, if you can or need to optimize the compiler work or see that the compiler is doing a good job. This was actually done fairly commonly in 90s and early 2000, but still it's a thing that you might want to consider. But anyway, the reverse engineering is part of re-engineering. So if you want to do re-engineering, you need to do also the reverse engineering job. And of course, considering that the reverse engineering gives you the information on the system right now, because maintenance corrupts the structure of the program. It means that unless everything is automatically handled, then it also means that you don't necessarily have the up-to-date information available everywhere. And there's a couple of examples here. So if we start with this, if you have never seen Goto example of source code, because it was told you everywhere that it's a horrible practice, we don't teach it here because it's a way to go insane. So this is what happens when you go Goto as source code. It's complete fucking nightmare. But if we are trying do re-engineering work on this, we simplify the system or make it more maintainable, we get something like this. Well, it's not exactly great work even now, but still, at least it's something that someone actually can understand. So the tools made it somewhat more maintainable, or at least somewhat more readable or usable. Also, some condition simplification. If we have the ability to re-engineer things and we see from the behavior that what's actually happening or what needs to be actually done, something like this can be reduced to something like this. Because this was generated by years of maintenance or someone doing really bad, patchy, technical depth job. And this was something that we came up with after we used the analysis tools to understand what actually needs to be done. So if we are doing maintenance or rehaul or re-engineering, also the simplification and getting rid of all the go-to examples and go-to modules and stuff like that is also something that we can do, if it's something that we still need to maintain. So, program restructuring. We use analyzer, we use graph builder, we use representations to understand what it's actually doing. Then we use generator or manual work or whatever we need to do, and we get the simplified version, the reduced complexity version of the software. There's tools to do that, also analyzer tools, analysis tools to support this sort of work if it needs to be done. And restructuring means that, of course, or reverse engineering means that we lose comments, we lose documentation, we have to give up something because we are restructuring things, so the documentation or the explanations of how things work aren't any more working, but still that's the price we have to pay. There's also different types of modules which do different things. So you might want to also consider that if we have something that works with the hardware, it might be a bit more annoying to revise or fix. Or if you are doing hardware transition, you know that you have to identify these so that you can actually even start things or understand if it's even feasible to do these fixes. Also, considering data, there's some problems. For example, legacy systems tend to use shared tables, global data, because simply on the older systems, this data privacy or systems to virtualize data management or use memory management units as an additional step or additional abstraction level between the hardware and the software simply didn't exist. So these sort of things also impose problems when you are trying to simply move or transfer old system to new system. This is also why the virtualization is so popular, because some stuff like Commodore or Amiga computers simply didn't have the resources. You had to use shortcuts, shared memory tables, shared global data, because there simply wasn't enough room to do anything fancy. And of course this skews everything, because we now have the resources or tools to do something more maintainable or usable, but it's simply no longer possible. There's also other things because of global data or shared objects, but you can read about those things from the additional sources on reverse engineering. Also, data imposes problems, like mentioned before, the data itself or the database management itself might actually be a similar size of problem as the software itself. But and these sort of things have to be considered if we are trying to update or re-engineer some legacy system to be useful today. There's ways of doing the data re-engineering. We are not going to go into this too much, first of all because it's a database management or database migrations type of problem, and you have courses on database management and database systems on this university, but at this point you need to remember or understand that the data re-engineering is one of the things that you have to take into account. And now that the classroom is saying that maybe I should probably stop speaking now, I'm going to skip a bit forward. We are almost at the end here. So, of course, with the data, you might also have to do cleanup, extension of migration work, but this is something related to the actual database management type. And of course, there's other things, but these are all data conversion and stuff is more or less about database management at these courses. So go there and ask from Antti Knutas about these issues. Tell him I sent you. Ask him to explain you how database management is handled in the reverse engineering scenario of migrating software project to another platform. He appreciates this and probably will also tell me some interesting feedback on this request. Anyway, well, there's more, of course, if we are working with the databases. If we have legacy systems which are not well supported, we might have a large problem, and actually the database approach or the data management scheme by itself might be a reason why re-engineering approaches are not always available or possible. So that's why you also have to do the analysis on the applied or used data before we merely go away to rewrite every Fortran code we can find with some new language or Java or something like that, because the database or the data itself might not be accessible. Anyway, from this lecture, reverse engineering and re-engineering, how these affect the situations when we are trying to rehaul existing system or migrate to new or other platform, or how these aspects or how these concepts affect the decisions on if we even can extend the life cycle of a software product. Finally, we had a vote, and based on majority vote, 67% of the students voted that these Monday morning sessions are not necessary. Of course, you audience here are the only people who have actually been coming here, even though we have 30 people on this course. So we will in future be doing this in a way that the lecture recording will be released on Monday, and we will not have a separate meeting here. Everything else stays the same. The visiting lecturer or the visitor lecturer will give his or her lecture here at 10 on Monday. I will be giving you a Moodle notification on when it's going to be, so we will have that as a normal lecture. That will not be a video, but my lectures will be given as a videos, and you can come to my office on Wednesdays to ask questions if you have problems or something like that. Also, the seminars will be given normally here by presenting your work here at the lecture room at Monday on the weeks that we will have the seminars, but on the course week 7 to 10, the rest of the theory lectures are given you as online videos, and if you have problems, send an email or visit me during my consultation hour. So that's that for this week. Next week we will not be meeting here because I will be putting a video online, and you can send me an email or visit my office if you have problems. Thank you.